All right, let's dive right into this explainer and explore the fascinating, high-stakes hunt for the missing 85% of our universe. For decades now, scientists have been tirelessly searching for dark matter, the invisible scaffolding of the cosmos. But what if, instead of looking for particles bumping into detectors in underground laboratories, we could actually detect dark matter by listening to the very fabric of reality ticking like a clock? Today, we're going to unpack some truly groundbreaking research that proposes sending quantum sensors into deep space to catch dark matter in the act of literally altering the laws of physics. We usually think of the rules of physics as these fixed, rigid pillars of reality. But what if they aren't? What if dark matter is actually washing over our solar system right now, almost like giant ocean swells, causing the fundamental constants of reality to slightly tick and change? It sounds straight out of science fiction for sure, but this is a highly motivated theoretical paradigm. If the universe is filled with a specific type of invisible field, the basic building blocks of nature, like the mass of an electron or the strength of electromagnetism, might be subtly oscillating all around us. And this brings us to a prime suspect: ultralight scalar dark matter. Unlike heavy, particle-like dark matter candidates, this is an invisible, wave-like bosonic field. It has an absolutely mind-bogglingly tiny mass, less than 10 electron volts. Because it's so light, it exhibits wave-like coherence across vast cosmic distances. If this scalar field couples to normal matter, it wouldn't just bump into it like a billiard ball. It would cause apparent oscillations in fundamental constants, like the fine structure constant, which dictates exactly how light and matter interact. Okay, moving into part one, the hideouts. Where are these gravitational atoms in our solar system? While we can't just go looking for this dark matter blindly, right? We need to know exactly where it's hiding in our own cosmic backyard to give ourselves the absolute best chance of detecting these tiny wave-like oscillations. It turns out, dark matter actually clumps around massive bodies to form what physicists call gravitational atoms. Just like an electron orbits a nucleus, these massive clouds of ultralight dark matter become gravitationally bound to large celestial bodies. If you look here, you'll notice how the specific mass and the corresponding Compton frequency, which is basically the oscillation rate of this dark matter wave, changes depending on if it's trapped by the Sun, Jupiter, Earth, or the Moon. Each celestial body captures a totally different frequency and mass, creating these unique, localized halos. Now check out the sheer scale of the density spikes on this chart. It's wild. The immense peaks near the Sun and Jupiter suggest that, due to direct capture mechanisms operating over billions of years, the density of dark matter in these specific regions could be many, many orders of magnitude higher than our local galactic background. If we were to fly a spacecraft, say zero point 0.1 astronomical units from the Sun or right up close to Jupiter, we could literally sail into incredibly dense clouds of this invisible substance. Which brings us to part two, the trap. Let's talk about the ultimate quantum rulers. So we know where the dark matter might be hiding, but how do we actually catch it? To feel these dark matter waves washing over us, we need the ultimate cosmic trap: insanely precise quantum clocks. Because dark matter causes the fundamental constants to oscillate, the actual ticking rate of a highly precise atomic or nuclear clock will slightly speed up and slow down as the wave passes through it. We are talking about mind-bending engineering here. To detect these shifts, we're looking for fractional frequency variations as low as parts in 10 to the 18th power. Just to put that into perspective, if a clock were that precise, it wouldn't lose or gain a single second over the entire age of the universe. That's the level of precision we need to see the tiny fingerprint of ultralight scalar dark matter. And to actually hit that level, researchers are looking beyond standard atomic clocks to proposed nuclear clocks. The crucial point here is this massive number, 5,900. It's the sensitivity enhancement factor, or K factor, of the proposed thorium-229 nuclear clock. While standard optical clocks have a sensitivity factor of around 1 or less, the unique energy level structure of the thorium-229 isomer makes it thousands of times more sensitive to variations in the fine structure constant. It essentially acts as a massive magnifying glass for the exact signal we're looking for. All right, part three, the code breakers. We're going to need specialized algorithms to catch these waves. Because here's the catch: having the best quantum clock in the universe just isn't enough. The clock is only the hardware. We also absolutely need the right quantum metrology algorithms to act as code breakers, to decipher the signal from the background noise. The standard way to read a quantum clock is an algorithm called Ramsey spectroscopy, where you let the atoms evolve over a long probe time to get a highly precise measurement. But there's a fatal flaw for our dark matter hunt here. Standard Ramsey algorithms can entirely miss the signal if too many dark matter oscillations pack into that long probe time. Well, actually, what happens is the ups and downs of the waves simply average out to zero. Dynamical decoupling, on the other hand, actively suppresses that background noise and inserts specific laser pulses to shift our sensitivity, letting us catch those faster dark matter frequencies without them just washing out completely. Take a look at this zero dead time differential spectroscopy setup. It's a really brilliant piece of engineering that circumvents normal laser coherence limits to extend the probe duration. It uses two clocks probed synchronously to cancel out correlated laser noise. That's fantastic for detecting very slow, low-mass dark matter waves. But as we were just talking about, it still struggles and loses sensitivity rapidly at higher dark matter frequencies because those fast waves are still averaging out over the extended probe duration. So narrowband dynamical decoupling, or NBDD, takes this a step further by inserting pi pulses at a constant, regular rate during the probe time. Every time a pulse hits, it flips the clock sensitivity. If you time these pulses to perfectly match the frequency of the dark matter wave, the signal builds up instead of canceling out. It acts exactly like tuning your car radio and listening super carefully to just one specific frequency. It's incredibly sensitive, but only if you already know exactly what frequency the dark matter is broadcasting on. And that is exactly the problem. We don't know the dark matter frequency yet. Enter broadband dynamical decoupling, or BBDD. Instead of evenly spaced pulses, BBDD inserts pi pulses at random times during the probe. By randomizing the pulses, you're effectively scanning the entire radio dial all at once to catch a wide range of unknown dark matter frequencies. It relaxes the rigid requirements on laser coherence and maintains sensitivity across a vast spectrum of potential dark matter masses. You can really see the power of this in the data right here. The broadband dynamical decoupling algorithm acts as the ultimate net. It maintains high sensitivity across a massive range, catching signals even out to the 10 to the negative 13 electron-volt mass range. Now, why does that specific number matter? Because that is exactly where the sun's dark matter halo density peaks. BDD is quite literally the key algorithm that makes detecting the sun's gravitational atom possible. Finally, part 4, the mission. Let's talk about space missions and what comes next. So let's recap. We've identified the dark matter hideouts, we've got the ultra-sensitive thorium quantum clocks, and we have the broadband algorithms to decode the signals. With everything ready, it's almost time to actually launch this investigation off the Earth and out into the deep solar system. Sending these quantum clocks and atomic spectrometers on spacecraft to Jupiter or the inner solar system is the next great frontier. But man, it comes with immense engineering challenges. For example, deep space telemetry is painfully slow, often less than 100 kilobits per second. You just cannot stream high-resolution quantum data back to Earth at dial-up speeds. It's going to require incredibly clever onboard real-time data processing, using tools like fast Fourier transforms right there on the spacecraft to compress the data before sending the signals home. Plus, utilizing techniques like Doppler-free cesium spectroscopy is going to be vital for these probes to achieve the sharp resonance required. The engineering is tough, no doubt, but the scientific payoff could literally alter our understanding of the universe. The stakes of this mission are completely unprecedented. As this quote hits the nail on the head, by leaving Earth's surface and flying directly into these gravitational atoms, those dense clouds of dark matter surrounding the Sun and Jupiter, our space-based quantum clocks will exceed the reach of Earth-based clocks by orders of magnitude. We aren't just looking slightly harder, we are taking the ultimate precision instruments and flying them directly into the heart of the mystery. And honestly, that brings us to the most exciting part of this entire endeavor. We are building the most sensitive listening devices in human history to catch the subtle ticking of dark matter. But it really leaves us wondering, once we deploy these incredible quantum clocks into the dark matter swells of the solar system, what other fundamental secrets of reality are we going to uncover? Whenever we build a totally new tool to look at the universe, we almost always find things we never even knew to look for.